Okay, this is video 7 in chapter 10. This will be the first video where I really start to talk about molecular shape, which is of course the title of the chapter. The previous discussion of Lewis structure was important though because these are very useful tools, as you'll see, in terms of deciding how the electrons are grouped around the atoms in a molecule, and particularly around the central atom, or the atom where you're trying to get a feel for the shape of the molecule at that point. The name of the technique that we use in chapter 10 is called, it's abbreviated VSEPR, which stands for valence shell, meaning outer shell, electron pair, pairs of electrons that we've been using, repulsion. And it's essentially, it's a theory or a model that essentially asserts that the shape of a molecule is determined by the fact that all the electron pairs involved repel each other, and therefore the shape of the molecule at the point that you're studying is shaped such that the repulsion, the electrons are as far away from, the electron pairs are as far away from each other as possible. Okay, and that actually will determine or dictate a shape of a molecule at various points in the molecule. And like I discussed when I briefly interjected ethanol a second ago, the shape kind of depends upon where in the molecule you're looking at. For a lot of these simple molecules that involve a single central atom and then a number of atoms that are bonded to it, the shape is simple. It's shaped around that central atom. But for bigger molecules, each part of a molecule will have its own shape. Okay, central to this theory is that for an atom that has multiple, let's say, how should I say it? For any central atom, a number of other atoms can be attached to it, or no, I should say a number of electron pairs even can be attached to it. Let me actually do this by way of example. So remember when we had carbon monoxide. Carbon monoxide was basically a carbon atom and an oxygen atom that were bonded together. And so essentially what we had were really only two atoms involved. And in that scenario, this is kind of known as a linear bond, meaning it forms a straight line. The angle between the two atoms is 180 degrees. Okay, but we had actually a third, which was, for example, when we had carbonate. Carbonate had in the center a carbon and then three oxygens around it. Okay, so in this case, the carbon bonded to three oxygens forms. I need to do it something like this, but actually formed a shape of a triangle. Each of the angles are 120 degrees. Okay. Then when we did methane, let's see if you can see this. Methane actually has four. Basically, it's a carbon in the middle and then four hydrogens around it, and it forms a shape known as a tetrahedral. Okay, and it's symmetric, no matter how you rotate it. There's an angle of 109.5 degrees at each angle, all symmetric around the center. Okay. You can even have a fifth and a sixth, and I'll demonstrate the fifth. I can't hold the sixth. I don't have enough real estate here. But the fifth is a shape known as trigonal bipyramidal, and it basically is you kind of look like it as a pyramid both above and below. The middle plane, if you will, has 120 degree angles, but the top plane, I guess, has 90 to the plane. Okay, and then there's even a sixth, which is known as octahedral, where you can have actually six atoms attached to the central atom. Okay. Now the book does a better job of this, and you can actually find good three-dimensional representations of these shapes as you go. But the key kind of takeaway here is that actually, by the way, when I said carbon monoxide as the first example, that was wrong. It was carbon dioxide. That was what I meant. Carbon dioxide is carbon's in the middle, and we got two oxygens on either side. Okay, carbon monoxide is known as a diatomic, and that doesn't really have much of a shape because it's really just it's just two things stuck together. So, kind of key takeaway here is that when discussing shapes using this model, there can be 2, 3, 4, 5, or 6 atoms attached to the central atom, and depending upon upon other factors involving the electrons, it'll force the molecule to have certain shapes. Okay. Now, what I want to actually draw a couple of things up here to show some examples of this. I think that's probably the best way to do this. I'm going to start with a couple of simple ones like methane. We drew methane before. Here's the Lewis structure for methane. The central carbon atom has 4 atoms attached to it, and what that will form then is a perfect tetrahedral, and that was the shape that I held up before. So, so when you have 4 symmetric atoms bonded to the central, it forms a tetrahedral. Okay. Now, I want to show another atom another molecule that's actually kind of similar in a way, and that is ammonia. So ammonia has a nitrogen pair. I'll draw it this way: a hydrogen, and a hydrogen. Okay. Here's ammonia, and here's methane. Now in this case, ammonia has only 3 atoms attached to the nitrogen has 3 atoms attached to it, and so the shape of this atom is not going to be tetrahedral. It's going to have a different shape. However, one thing, and this is actually really important, is that if you think about it just from the electron standpoint, the central nitrogen atom really does have 4 things around it. It has the things meaning electron pairs. It has the 3 bonding pairs to the hydrogen, but it has this lone pair also. So truly from an overall shape, thinking about the electron configuration, ammonia has a very similar shape as methane, meaning that we've got a pair of electrons up here, and we've got 3 more pairs of electrons in the other 3 directions. And so from an electron pair repulsion standpoint, this pair of electrons is repelling this pair of electrons, this pair of electrons, and this pair of electrons. So even in this case where we have ammonia, we have 3 atoms, there still is 4 pairs of electrons that are repelling each other in this molecule. Okay, this is actually very important because I think what you'll see in an awful lot of, and we're going to do a lot of examples going over here, but what you see in a lot of these cases is for many of these atoms, that we see in covalent bonding, they're like carbon and nitrogen and oxygen. You'll see an awful lot of common themes that run through it, and this kind of shows one of them. Now, so here's a case where we actually have 4 pairs of electrons around each atom. Let me show you another one though, which is carbon dioxide. Okay, so in carbon dioxide, in this molecule, the central carbon atom has 2 things attached to it, and the electron clouds, even though they're double bonded, there's a big electron cloud on one side and a big electron cloud on the other, and they want to repel each other, so they want to be as far apart from each other as possible. Here's a case where the central atom really only has 2 things, 2 electron configuration things, or 2 electron groups or clouds, whatever we want to call it, that is bonded to it, and therefore it forms a linear shape. So in this case, unlike the ammonia case, which had 4, here we only have 2 things. Okay. Now, so this will have a linear shape. I should have circled that. I want to compare carbon dioxide though to water. Water. Let me We'll erase that thing. Water is good old H2O. And from a Lewis standpoint, we draw it like that. And don't forget, oxygen has 2 pairs. And we could actually go through the formal way, the whole Lewis structure technique to show that this is indeed the case. We add up all the electrons. We do an octet verification. Sure enough, the middle has an octet, etc. So this is a good Lewis structure depiction of water. Well, what's interesting here is that if you ask yourself, well, how many things are bonded to the central oxygen atom, your first reaction would be 2, because you got 2 hydrogens, right? But really, when you in the bigger picture, when you think about electron clouds anyway, there are really 4 things, because there's this pair, and then these 2 pairs. So even with the in water, the central oxygen atom is surrounded by 4 pairs of electrons that all repel each other. And so if you just look at the electron clouds themselves, it's basically kind of roughly tetrahedral, the electron configuration, that is. But if you look at the molecule itself, the molecule is actually bent. In fact, that's the word one of the terms they call the shape is that the water molecule has a bent shape, because just focusing on the atoms and ignoring the pairs for the moment, the electron pairs up here want to repel the electron pairs down here, so it forces the bonding electrons to the hydrogens to be repelled from the lone pairs, and they take on this overall tetrahedral shape. But looking at the molecule, it's a bent shape. Okay, I'm going to end this one and then go on to part 2 of the VSEPR theory in the next video.